Before we really get into the stuff of grade 11 math, we need to talk about radicals. Yes, this will be a review, so it'll probably be kind of tedious, but I don't think too many of us bother to remember what the radicand refers to. I didn't, back in the day. Fortunately, it was not exactly tested of us. So, the radicand is a number or expression under the radical sign. So, square root of whatever, or cube root of whatever, the whatever part, is the radicand. Now, the entire radical is a radical in the form of root, or however many root of n, where n is some number. Now here we said n or x is greater than 0 because, well, technically speaking it could be equal to, but there's not really much point of writing, square root of 0, because that is just 0. So an entire radical would be this with some number underneath. For example, here or here. Why is it that here we must be greater than 0? It's because we have an even numbered root. If we had an odd numbered root, it could be positive or negative as a radicand, it wouldn't matter. Now a mixed radical is in the form of m root n, or m times whatever's the root of n. This is different from a mixed fraction in concept because you multiply these things together. In mixed fractions, like say, 1.5 or a third or whatever, this is added together instead of multiplied together like this. Now, why is it that m is not supposed to be plus minus 1? It's also not supposed to be 0, really, but usually that's not mentioned too much because you would just write, 0 times something is equal to 0 when it's simplified. Whereas if you have plus minus 1, well, you're just going to put a plus sign or a minus sign. We point out that for the most part, the default for radicals is to find the positive root, like root 3. Well, what can you multiply together to make 3? You can multiply positive root 3 times positive root 3, or negative root 3 times negative root 3. So, which one should we choose? Well, actually, you should have two possibilities, but when you graph it, you usually only graph the positive one, unless the question specifically shows that x equals y squared or something, instead of y equals square root x. At least that's a convention in Canada. Regional conventions will vary. For example, if I recall correctly, in East Asian countries, when it's a root, it means plus minus. An irrational number is not a number that is nonsense. It is very reasonable, it has some value, but it cannot be expressed in the form of a over b, where a and b are integers and b is unequal to 0. What this means is that you have an infinitely long, non-repeating decimal. Because if you have two integers dividing one another, you will inevitably, eventually get yourself a repeating decimal. Pythagoras, a Greek mathematician, his students and himself came to a conclusion that there were numbers that could not be explained using fractions. Now, the conclusion that I said he and a few other mathematicians worldwide came to was Pythagorean theorem. Pythagorean theorem. There are records that the Egyptians were aware of at least parts or some examples of this rule, and so was East Asia long before Pythagoras' time. But the expression of these numbers that could not be expressed by fractions, well, that was one of the things that Pythagoras kind of got a head start on in terms of codifying the concept of irrational numbers. Now, irrational numbers does not mean not real. Irrational numbers are still real numbers. So not real numbers would be, say, square root of -1. That's imaginary numbers. Okay, let's do some examples of some basic operations with radicals that we need to know for grade 11. So square root 5 times square root 5 gives us, well, we can just write 5. But technically speaking, the actual train of thought that we should have followed was square root of 5 times 5 equals square root 25 equals 5. Now in this case, we still follow the convention that the root is assumed to be positive. Otherwise, we could be like, oh, this could be plus minus 5 because square root 5 could mean negative square root 5. Well, that's a little bit more complex than we are going to bother with. So, for this, square root 11 times square root 22, we have this is equal to 11 square root 2. Why? Because this breaks down to square root 11 times square root 2 times square root 11 equals 11, well, 11 root 2. Okay. So, here we have root 60 times root 15. Now, what does this equal? Well, we can see that this is equal to 4 times 15 times 15. If we aren't completely sure at a glance, we should take our time to get a good look, yes? So, square root 4 times 15. Why is it that some people like to use brackets for multiplication instead of just using the old multiplication symbol we learned back in elementary school? Well, it's because when you have radicals and your radical is just a little bit too long and you put a multiply symbol, it's easy to mess up. That's why a lot of people like using brackets. So it is 2 times 15 and that's 30. Of course, we could have looked at this and be like, oh, 4 times 15, okay, that's 2 root 15 times root 15, okay, 2 times 15, 30. And pretty much gone, relatively speaking, almost straight to the answer, but the actual thought process is as I listed here. Now here, let's express these in the simplest form. Now the entire radical is not in fact the simplest form. It's not the easiest way we can use something. The easiest way we can use something is to express it as a mixed radical. So here, this is equal to 2 times 9. This is equal to 3 root 2. And this next one here, 363. Now suppose we don't know where to start. So if we don't know where to start, what can we do to find how to simplify a radical? Okay, let's do some factoring. I should put a label here. Factoring. Yay. So, when we factor this, we divide by 3, and then we get 121. And we divide by, well, hey, wait a second. 121 is 11 squared. This is then equal to square root of 3 times 11 times 11. So that's 11 root 3. Now the next step is root of 500. So what do we know about 500? Well, it's 5 times 100, and 100 is 10 squared, yes? So depending on how much your teacher is willing to let slide, instead of forcing you to show all the steps, you can just go straight to 10 root 5. And of course, how much your teacher is willing to let slide usually depends on how much they reckon your experience level is. So example 3, add or subtract radicals. When you have to add or subtract radicals, you want to make sure that the radical portion is the same. Otherwise, it would be like, 2x plus 3y. How can we add this? We can't unless we can express one in terms of the other. So we can only add 2x plus 3x equals 5x, yes? So here, 9 root 5 plus 7 root 5 is 16 root 5. And down here, we have 10 root 3 minus 7 root 27 equals, well, this is not the same as that. How can we make it the same? Well, 27 is 3 times 9. So this is equal to 10 root 3 minus 7 times 3 root 3. Of course, you could probably get away with just writing 21 root 3, but we're being very, very cautious here. So 10 root 3 minus 21 root 3 is equal to negative 11 root 3. What about this example here? Well, we see that none of them have the same radicand. So what we should do is make them have the same radicand. So if we're being exceedingly cautious, we get something like this, because 20 is 4 times 5, and 4 is a perfect square, minus 3 over 7, 5 root 5, plus 6 over 7. 5 times 9 is 45. 9 is a perfect square. Although it does take some experience to recognize these things, if you happen to not recognize them right away, do the factoring I showed you earlier. The vertical step method, or whatever it's called in your area. There are many methods to factor, and honestly, the tree method that I've seen sometimes before is one of the dumbest ways possible to do it, at least by my personal experience. It's better to pry out one prime factor at a time, instead of take up like half a page of horizontal spread. Okay, so 6 over 7, 3 root 5. So this is going to be 12 over 7 root 5 minus 15 over 7 root 5 plus 18 over 7 root 5. So this is equal to 15 over 7 square root 5. Improper fractions, some teachers frown upon them. Others, well, they really could not care less. Okay, example 4. Multiply by using the distributive property. That means we need to show each term being multiplied separately. Thus, this is equal to 2 root 2 times root 2 plus 2 root 2 times negative 3 root 3 plus root 3 times root 2 plus root 3 times negative 3 root 3. So this is equal to 4 minus 6 root 6. And here we have root 3 times root 2, which is equal to root 6 plus this thing. So that comes out to negative 3 times, well, root 9, which is so this comes out to be negative 5 root 6 minus 5. Now, if it had been a plus b times a minus b, where a and b are terms, we could have done just a squared minus b squared. But since it wasn't, we had to do it the long way around. Here we have a more challenging problem than average. So here we have root 128 equals to root 2 plus root x. What is the value of x? Equals root 128 minus root 2. What is root of 128? Well, we know that 8 times 8 is 64. And what is twice of that? So 8 root 2 minus root 2 equals 7 root 2. So that's root of x. Then x is equal to, well, we could write bracket 7 root 2 squared, or we could write something like this, 7 squared times 2. What is 7 squared? It is 49, and therefore this is 98. The value of x is 98. I should point out that if this problem was more complex in the sense that you couldn't get these down to the same radicand, you could always just take this whole thing, like say minus root 3 or something. You can take the whole thing and then square it. And then you'll find x, with a lot of radical signs probably mixed in the middle, but you'll have x. So That's it for this section. Hopefully we've managed to review radicals, radicands, mixed radicals, entire radicals, or whole radicals, depending on where you live, and of course the concept of irrational numbers. Hopefully we've reviewed these concepts enough that we will not have any problems with them going forward. So see you next section then.